Okay, I'm going to start this lecture by finishing Chapter 11. I'm going to cover Section 11.8, Intro 4th edition of his book, Principles of Chemistry, A Molecular Approach. We're going to go over molecular orbital theory, and then when we're done with that, we'll cover Chapter 12. And I will do a separate video for working problems out of the book. I'm just going to present lecture material in this video, and then the other video will be working problems. Enough of you watched my second video from last time of me working problems. I'll go ahead and do that again. In any case, we're in the middle of Chapter 11, toward the end, and what Chapter 11 is all about is advanced bonding theories to explain all our observations rather than just some of them or most of them, because we want to be able to explain everything we see, not just some of it. Because in Chapter 10 we went over ionic and covalent bonding, which you learn in your introductory chemistry class, and that's fine. It explains a lot, but not everything. So we've gone over valence bond theory and hybridization orbitals, because that helps us to explain why some compounds break the octet rule. Because in Chapter 10, we learned how we can break the octet rule, but really didn't go into the why or the how. And we're covering that in Chapter 11. So we're going to do molecular orbital theory next, because we've gone over several bonding theories, but they still don't explain everything. And we want to be able to explain everything. Okay? So molecular orbital theory invokes a lot of ideas from a lot of different areas, lots of different things we've already discussed in class, and pushes them together to mold them into a new theory on bonding. So what we need to know about molecular orbital theory is, instead of having atomic orbitals that overlap or atomic orbitals that are mixed, now we have a new kind of orbital, molecular orbitals. These are orbitals that represent the entire molecule. That's why they're called molecular orbitals rather than atomic orbitals. Now, molecular orbitals have a lot of the same characteristics of atomic orbitals, meaning you have a maximum of 2 electrons per orbital. If you have 2 electrons in the same orbital, they need to have opposite spin. Orbitals have definite energy levels. And we can visualize molecular orbitals with electron density contour diagrams, just like we did before. I'm not an artist. I can't draw those. I don't expect you to, because I don't expect my students to do anything I can't do. Don't worry about drawing stuff. All right? Okay. So one idea we're going to grab from quantum theory is the idea is that when electrons come together, they interfere with each other. Remember that double slit experiment we watched? Where electrons are so small that the wave properties become extremely important. When you're very large, like the size of my table or myself, the wave properties of me are not important. The wave properties of my table is not important. But when you get things that are very, very tiny, the wave properties become extremely important, like they are for electrons. So we saw in Chapter 7, I believe it was 7, on quantum theory about how electrons interfere with each other because they have wave properties. Now there's 2 ways that waves can interfere with each other. So we went over this too. If the peak and the trough of the waves are in phase, they will have constructive interference and they add together. And then we get a bigger wave, which translates into higher intensity. If these waves are out of phase, the trough and the peak coincide, then they cancel out. That's called a destructive combination, destructive interference. So constructive interference, the waves are in phase and they add to each other. If they're out of phase, they cancel out. So we're going to use these ideas of constructive and destructive interference and insert that into a bonding theory. So when we talk about molecular orbital theory, we now have new kinds of orbitals that are based upon this idea of constructive interference and destructive interference. So when 2 atomic orbitals overlap to make a molecular orbital, you're going to make 2. You're going to make a bonding orbital from constructive interference where the waves are in phase. And you're going to make an anti-bonding orbital to represent when the waves are out of phase. Okay, so now we have different kinds of orbitals, something we haven't seen before. Bonding and anti-bonding. A bonding orbital contributes to the strength of the bond. Anti-bonding orbitals are destructive, so they work to break the bond. So if you have more bonding orbitals occupied than anti-bonding orbitals, then you've got a bond. But if you have equal amounts of bonding and anti-bonding, then the bonding and anti-bonding cancel out and you have no bond, you have no molecule. What's interesting about these anti-bonding orbitals is they have destructive interference in that there's a node between the two atoms in your bond where there's 0 electron density. And this serves to try to negate the bond. Okay. So where we have direct overlap of orbitals, we have a sigma orbital. So now we're going to invoke those same ideas of head-on and sideways overlap that we talked about with hybridization theory. So sigma bonding orbitals are still head-on overlap. And you get two kinds of sigma orbitals, bonding and anti-bonding. When you have anti-bonding, you get this star. So here's a bonding. You can give it a little b or not. It's up to you. But we give it a sigma for head-on overlap. And if we're anti-bonding, we give it a star. Your anti-bonding orbitals are always higher in energy than your bonding. Okay. So here's an example of sigma bond, a bonding orbital, and an anti-bonding orbital. So let's say, for example, I have two hydrogen atoms coming together to form a bond. They each have one electron in their 1s orbital. They will get head-on overlap, and now here's my molecular orbital. I call this sigma 1s because the electrons originated in the 1s orbital. Here's my bonding with high electron density between the nuclei. Here's my anti-bonding orbital, higher in energy, with this node of 0 electron density between the atoms. So the question is, which orbitals are occupied and which are empty? Remember, each orbital holds 2 electrons. So I have a total of 2 electrons from my 2 hydrogens. So my bonding orbital will be full with 2 electrons, and my anti-bonding orbital will be empty. So I have a stable molecule for my hydrogen molecule. We always have increasing energy going up. Anti-bonding orbitals are always higher in energy than your bonding. And just like we did before with the off-bow principle, the low energy orbitals get filled first. So we start at the bottom and we work our way up. So here's an example of molecular orbitals for a visualization of them for hydrogen, the hydrogen molecule. All right, here's a way that we represent the same thing on paper, because we're not terribly good at drawing in 3 dimensions on paper, so don't worry about that. This is how we usually represent a molecular orbital diagram. And I mentioned previously we need to go over how to do orbital diagrams, because we need these to make a molecular orbital diagram. So I have my orbital diagram on either side for my atoms. I bring them together and I make my molecular orbital diagram. So this whole thing is what you need to write for your molecular orbital diagram. You represent each atom individually on the left and the right, and you represent your molecule coming up the middle. So for my hydrogen molecule example, here's one hydrogen atom with an electron in the 1s orbital. Here's my other H atom with his electron in the 1s orbital. They come together, they overlap, they make the molecular orbital. Here's my sigma bonding with 2 electrons in it, called sigma 1s, because my electrons came from the 1s orbitals. And here my anti-bonding orbital is empty. I call it sigma 1s star. And we draw these little dashed lines so we can see where the electrons are going when they fill the molecular orbitals. This is a typical molecular orbital diagram for hydrogen. And we can give these guys electron configurations, just like we do for atoms. So when we're using molecular orbital theory, my electron configuration for H2 is sigma 1s with a superscript 2 to show that there's 2 electrons in my sigma 1s orbital. Now we're going to introduce another concept, something new. that's unique to molecular orbital theory, which is bond order. Bond order gives you an idea of the strength of the bond. The higher the bond order, the higher the bond strength. Now, what's different about bond orders with respect to the other ways we have discussed bonds, single, double, and triple, is we can have fractions. We can have a bond order of 2.5 or 1.5, and this is fine. Still a stable molecule. This is not a big deal. But the way we calculate bond order is we take the number of bonding electrons, so those are my electrons in my bonding orbital, subtract off the number of anti-bonding electrons in my anti-bonding orbitals. So subtract anti-bonding from bonding, multiply by 1/2. That's my bond order. So in this example here, I'm doing the hydrogen molecule. I have 2 electrons in my bonding orbital. My anti-bonding orbital is empty, so 2 minus 0. So I subtract 2 minus 0 is 2, multiply by 1/2, and I get a bond order of 1, which is what I would expect because a H2 molecule has a single bond. So if you have a molecule with a single bond, he'll have a bond order of 1. If your molecule has a double bond, you'll have a bond order of 2. You can get fractions when you get into things like ions, and we're going to go over that in a few minutes. But remember, your bonding orbital is always lower in energy. Your anti-bonding orbital gets the little star. And we fill these orbitals just like before. We start with the lowest energy level, and we work our way up. Half the battle with doing these molecular orbital diagrams is getting the number of electrons correct. That is half your battle. So, because you see here in this diagram, I have 1 electron on the left, 1 electron on the right, so that means I need 2 up the middle. Okay, always keep track of your electrons and make sure you've got the right number of electrons showing. Again, that's half the battle with these diagrams. Get the number of electrons correct. All right, onward. So we can use molecular orbital theory to make predictions. Can a diatomic molecule of helium form? Well, let's try it out with a molecular orbital diagram. I have 2 helium atoms coming together. They each have 2 electrons in the 1s orbital. And when I bring them together to form my bonding and anti-bonding orbitals, I have 2 on the left, 2 on the right, so I need 4 up the middle. I can't have any electrons wandering off, okay? So if I have 2 in my bonding and 2 in my anti-bonding, my bond order is equal to 0. 2 minus 2 times 1/2 is 0. If I have a bond order of 0, I have no molecule. The bond doesn't exist. The molecule does not exist. So this tells you about the predictive power of molecular orbital theory. Again, I'll be working problems in a separate video, but I will be doing 11.9, which is all about drawing molecular orbital diagrams and bond order. The idea behind bond order is, if your bond order is 0, you have no bond, you have no molecule. If your bond order is 1/2, like say I removed one of these electrons and made an ion, I would have a bond order of 1/2, and I would have a very short-lived molecule. It's pretty unstable if you have a bond order of 1/2. It might stick around for a second or so, maybe not, maybe a fraction of a second, but it's going to be unstable. To have a stable molecule, your bond order has to be at least 1. Then you know you've got good stability. If it's 1.5, also fine, stable. Fractions are okay. You just got to be 1 or bigger to be a stable molecule. Okay. All right, so let's move on. Now, we've only been talking about elements in the first row so far. So now let's start talking about elements in the second row. If we're in the second row, now we have s and p orbitals for shell 2 to worry about. So what's going on with the p orbitals? If you have head-on overlap, you get your sigma bond. So here's my sigma bonding and my sigma anti-bonding. Notice the node in the middle. But with my other p orbitals, I'm going to have sideways overlap, and that gets me pi bonding. Remember, we get the pi bonding when we have double and triple bonds. That still holds true here. If I've got pi bonds forming in my molecular orbital theory, I do have multiple bonds. So I've got head-on overlap for my p orbitals to make an s bonding and sigma bonding and sigma antibonding. And then with my other p orbitals, I'm going to do this sideways overlap. There's my bonding pi orbital right here. Here's my anti-bonding pi orbital. Again, if you're bonding, you contribute to the strength of the bond. If you're anti-bonding, you're going to destabilize the bond because you have this node in the middle with 0 electron density. So here's my head-on overlap, here's my sideways overlap. Sigma orbitals, pi orbitals that originate from p electrons. Electrons in p orbitals. All right, so let's move on. So now we're going to incorporate this idea of p orbitals being able to do a head-on overlap to make sigma and sideways overlap to make pi. And this is your typical molecular orbital diagram you're going to see for the second row for electrons in your second shell. Here's my 2s electrons here. They can only do head-on overlaps. I got sigma bonding and sigma star. You'll notice the sigma has a subscript of 2s, meaning these electrons came from 2s atomic orbitals. So here's my 2s electrons that will reside here. For my 2p electrons, remember the p orbitals can have head-on overlap for sigma. So here's my sigma bonding, here's my sigma anti-bonding up here. Then in the middle I've got my pi bonding and my pi anti-bonding orbitals. So your p atomic orbitals can come together in two ways, head-on to make sigma or sideways to make pi. All right, so I've got 3 bonding and 3 anti-bonding orbitals from my 6 p orbitals, 3 on either side. Remember, on each side we represent the atoms, and my molecular orbitals go up the middle. And we start with the bottom orbitals, the lowest in energy, and we fill them up from there. Okay. Now, sometimes the ordering of these orbitals can change. And the justification for this is that we say, okay, there's some interaction going on between the s and the p orbitals. And when that happens, that will lower the energy of sigma 2s, and it will raise the energy of sigma 2p. So when this happens, my p orbitals are lower in energy than my sigma from the p. Here's sigma s, sigma star s, pi 2p, sigma 2p. So now my sigma is higher in energy than my pi orbitals. And I'll show you, it says right here, showing you here when this happens. If you're on the left side of the p block on the periodic table, so boron, carbon, and nitrogen, you will get this ordering here where the pi orbitals are lower in energy than the sigma from your p electrons. If you're on the right side of the p block, you go in this order here for oxygen, fluorine, and neon, where your sigma bonding from the 2p are lower in energy than the pi bonding. So you get this flip here depending on what side of the p block you're on. So on the right side of the p block, the sigma 2p are lower in energy. On the left side of the p block, the pi 2p are lower in energy. And then you'll still have your anti-bonding orbitals up here. All right, so here's another illustration of the same thing. Here's the left side of the p block on the periodic table. We have large 2s2p interactions. You get this flipping of the energy levels. So for boron, carbon, and nitrogen, your molecular orbital diagram will look like this for shell 2. Here's my 2s, anti-bonding 2s, pi 2p, sigma 2p. For boron, I've got 6 electrons, so I'm going to fill them in like so. I'm still following the Hund's rule, 1 electron per box before I can fill them up. All right. So, and we fill in our molecular orbitals as we go from B2 to C2 to N2. Okay, and look what we have down here. The bond order goes from 1 to 2 to 3. N2 we know has a triple bond. It's showing a bond order of 3 using molecular orbital theory, and so those match. You'll also notice the bond enthalpy. That's the energy you have to put in to break the bond. The higher the bond order, the higher the bond enthalpy. So the higher the bond order, the stronger the bond, the more energy you have to put in to break the bond. Also, we have here bond length. As bond order goes up, the bond length gets smaller. And that agrees with what we discussed in the previous chapter. When you have double and triple bonds, you get a shorter bond. Okay. And at the bottom, we see here, we're predicting magnetic behavior. Are we paramagnetic and we're attracted to a magnet? Or are we diamagnetic and we're slightly repelled? So this is some of the predictive power of molecular orbital diagrams. If I've got unpaired electrons here, I'm paramagnetic, just like we've talked about before. For C2 and N2, these guys are all paired up, diamagnetic, slightly repelled by an electron. All right, so here's the left side of the p block, boron, carbon, and nitrogen, where the pi orbitals are lower in energy than the sigma. Now here's the right side of the p block, oxygen, fluorine, and neon. You'll see here for neon, all my boxes are filled, all my bonding and all my anti-bonding are filled. When that happens, the anti-bonding and the bonding cancel out. You have a bond order of 0. You have no molecule. The diatomic molecule for neon does not exist. That's why we don't have any data on the bond strength or the bond length or magnetic behavior. This is not a thing that happens. And molecular orbital theory verifies this. Now here's F2 right here, and here's O2. But look at the surprising thing about our oxygen molecule. I've got unpaired electrons. I'm paramagnetic. I have never seen this with any other bonding theory. We have never seen this with any other bonding theory we've seen in our class. Every other bonding theory shows paired electrons for O2. But look here, we have unpaired electrons for O2. So molecular orbital theory is predicting that O2 will be attracted to a magnet. Okay, I already went over that part. All right, so you'll remember if we're diamagnetic, all our electrons are paired up, and we're weakly repelled by a field, the magnetic field. Paramagnetism is when you're attracted to a magnet and you have unpaired electrons. And as we saw in the previous slide, oxygen molecule, O2, has unpaired electrons. And yes, it is indeed paramagnetic. Again, this also demonstrates the power of molecular orbital theory. It predicts oxygen will be attracted to a magnet, O2 molecule. None of the other bonding theories we've talked about predicts this, but it really is paramagnetic. Okay? So what this picture is trying to show here is someone pouring liquid oxygen between a magnet and it's attracted to the magnet. It's kind of a lousy picture. I highly recommend you watch this YouTube video that demonstrates that yes, liquid oxygen really is attracted to a magnet. It is paramagnetic. Molecular orbital theory is correct. Okay? What we're going to do on Monday when we start lecture, I'm going to play this video for you. So either watch it on your own or watch it in class. But it's a really good video that demonstrates, and you can really see it for yourself. It's a live person doing a real thing of pouring liquid oxygen over a magnet, and it's attracted to it. That's what this guy is trying to show here. It's a very cool video. In any case, in my separate video, I will go over 11.10 in the book, which is on page 479, intro. All right, onward we go. Now, what we've talked about so far is diatomic molecules where both atoms are the same. Now we're going to talk about what if I have different atoms in my molecule, like nitrogen monoxide, NO. This is what comes out of the tailpipe of your car. Like we've talked about before, NO has an odd number of electrons. And this shows up here as a single electron in a pi antibonding orbital. It's a radical, very reactive because of that unpaired electron. But the way you do a molecular orbital diagram where you have two different atoms is when you have a more electronegative atom, the electrons are closer to the nucleus, so that makes them lower in energy. That makes the molecular orbitals lower in energy as well. So you can see how with my molecular orbitals theory, molecular orbitals here, they have lower energy than they would have been if this had been N2. So these are all lower in energy and they match more closely the energy levels of the atomic orbitals. again, half the battle in drawing these molecular orbitals is getting the correct number of electrons. I've got 5 valence electrons for nitrogen, so I've got 5 arrows here. I've got 6 arrows here for 6 valence electrons on oxygen. So 5 plus 6 is 11. I've got 11 arrows up the middle. Keep track of your electrons. It's half the battle. All right. So that's it for chapter 11. Now we're going to move on to chapter 12, which is different topics. And I'll cover what you need to know for the final. So chapter 12 is all about liquids, solids, and intermolecular forces. Previously in the semester, we talked about gases. Now we're going to talk about liquids and solids and what holds them together, our intermolecular forces. You'll remember from our chapter on gases when we talked about ideal behavior versus real behavior. When we have real behavior of gases, there are attractions between a molecule and his neighbor. Those attractions are what we're going to talk about in chapter 12. Those are called intermolecular forces. An attraction of one molecule that has with its neighbor. And this has all kinds of consequences, especially melting point, boiling point, viscosity, etc. So lots of consequences to intermolecular forces, and we experience them in our real lives every day. And I'll give you some real world examples of some of these forces as we come across them. All right. So first we need to talk about states of matter. And why are some compounds a solid, why a liquid, and why a gas at room temperature? Well, first let's just remind ourselves about our states of matter. It's been a while. But the difference between states of matter here, why are some solids, some are liquids, and some are gases at a particular temperature? And that has to do with their intermolecular forces. If you're a solid, you have stronger intermolecular forces holding you together. If you're a liquid, they're a little bit less. And if they're a gas, your kinetic energy dominates your behavior rather than your intermolecular forces. So keep in mind, when we have a gas, we have large distances, relatively speaking, between molecules. If we have a liquid, the molecules are touching, but they can slide around each other, which is why liquid has flow. In a solid, the atoms or molecules are touching and they're not moving very much, but they do have a tiny bit of a wiggle. Remember, everything's got a little bit of a wiggle. If you're solid, you're not going to see the wiggle, but don't worry, it's still there. Everything's got a little bit of a wiggle. If you want to get rid of all the wiggle, go to 0 Kelvin. Then you have no wiggle. In any case, your solids and liquids are called condensed phases because your molecules and atoms are touching. A gas is not a condensed phase because you've got these large distances between the molecules. Okay, so onward. So let's go over the properties of solids, liquids, and gases. These are our 3 basic phases that we come across in our everyday life. There's more phases than just these, and we're going to go over them in this chapter. That's one of the cool things about this chapter. We can cover supercritical fluids and stuff like that, which is a lot of fun. All right, so let's go over some properties real quick of our 3 basic phases that we come across in everyday life. First, volume and shape. Solids have definite volume, definite shape. My chair is not going to grow, and he's not going to turn into a table. My chair stays a chair, and it stays its size. Definite volume, definite shape. For liquids, I have definite volume, indefinite shape. I can have a cup of water in a bowl or a cup of water in a glass. The liquid takes on the shape of the container. My water will be bowl-shaped or it'll be glass-shaped. But it's still a cup. That won't change. A cup of water is a cup of water no matter what container it's in. Now with gases, indefinite volume, indefinite shape. They take on the volume and the shape of their container. Okay, regarding density here, solids are high in density. Liquids are high in density too, with one exception. Water is an exception. We'll go over that later. Gases have low density, again, because of those large spaces between the molecules. Compressibility. Can I squeeze these molecules or atoms together? Solids and liquids have small compressibility. Gases are very compressible because we can shrink those large spaces between the molecules. Regarding thermal expansion, meaning things get bigger as you warm them. Solids have very small thermal expansion, but they do have it. This is why we have cracks in the sidewalk, because the cement will expand on a hot day, and the cracks give the cement room to expand and then contract again on a cold day, so we don't break the cement. All right, liquids also expand when they warm. We see this big impact here with thermal expansion of liquids with global warming, because as the oceans warm, the volume of the ocean will increase, and that contributes to ocean level rise, sea level rise. Okay, so that's a problem. But that's a real thing that really happens. It's just plain old physical chemistry or physics. Gases expand a lot more than liquids and solids. And again, we went over with our chapter on gases. We see the effect of thermal expansion on gases with our hot air balloons. We fire up the burner, the gas expands to inflate the balloon, and away we go. Regarding flow, solids don't really have kinetic motion, but they do have a little bit of a wiggle, but that's it, just a little bit of a wiggle. They don't flow. They're pretty much stuck in one spot. Liquids do flow, and gases really flow. Regarding diffusion, the ability to travel through a solid, liquid, or gas. Solid, you can get diffusion, but it's super slow. Liquids are also, you get some diffusion, but it's slow, but you can speed it up if you heat it. And then gases, diffusion is very fast, because as we went over in our gases chapter, these gases travel very fast. If you remember that one calculation we did for our oxygen molecule at room temperature, they were moving several hundred meters per second. These things really move, so that makes the diffusion super fast. Okay, so how do we know, or why is it, rather, something is a solid or liquid or a gas? Well, it's a balance between the kinetic energy of your particles and your intermolecular forces, the energies between particles. So if you have a gas, you have large kinetic energies compared to the energy of attraction. If you have a liquid, your kinetic energies is about the same as the energy of attraction. And if you're a solid, your energies of attraction dominate and you don't move much. So you have small kinetic energy. So now we're going to talk about the energies involved here between one particle and another. Those are called intermolecular forces. Those are the forces between a molecule and his neighbor. Now, these intermolecular forces are not nearly as strong as the bonds within a compound, but they do have impacts. They impact boiling point, melting point, viscosity, surface tension, capillary action. So we're going to go through weakest to strongest of our different types of intermolecular forces, and then I'll go over them in more detail. The weakest intermolecular force are called dispersion forces, or also known as London dispersion forces, because London was the scientist who did a lot of work in this area. And we always like to name stuff after people, especially people who do cool things. The next strongest intermolecular force is dipole-induced dipole. Not in your book, but it should be. I say that a lot about a lot of different books. Oh well. Because, yeah, in the book it goes straight from dispersion to dipole-dipole. But there's another one, dipole-induced dipole, not in your book. Also not in your book is ion-induced dipole, meaning an ion can induce a dipole in his nonpolar neighbor. Not in your book, but it should be. Okay, next is dipole-dipole interactions, which is in your book. And then we have hydrogen bonding, which is a special kind of dipole-dipole interaction, which is very strong. And then we have ion-dipole forces. Ion-dipole interactions are the ones that are responsible for dissolving ionic compounds in water. So first we have the weakest of our forces, which is the dispersion force. Every atom, every molecule, every species shows dispersion forces. Sometimes these dispersion forces dominate and sometimes they don't. Sometimes other forces take over. But everything has dispersion forces. So what's going on here with dispersion forces is, let's say I have two nonpolar molecules like H2. Okay, now what happens with these guys? Well, what we talked about previously is that electrons don't orbit the nucleus like planets orbit the sun. They have wave properties, right? And these electrons can kind of slosh around. So what can happen in a nonpolar molecule is temporarily we can have a negative end where all the electrons are at one end, and then a positive end where we have low electron density. This is a temporary situation in a nonpolar molecule. But if this happens, and it does, he can induce a dipole in his neighbor, and now you've got this situation. So this tendency of this electron cloud to distort is called polarizability. And we're going to go into what makes a molecule more polarizable or less polarizable. So let's go into what impacts the polarizability of your electron cloud. How easily can I distort it? Okay, the first thing is number of electrons. The more electrons you have, the more dispersion force you have. So the more electrons you have, the more you can distort the electron cloud. So first, number of electrons. Number two, the size of your atom or molecule or your molar mass. The bigger the atom, the bigger the molecule, the higher the molecular weight, the higher the polarizability, which means you have a stronger dispersion force. The last thing is the shape of your molecule. If you have molecules with similar masses, the shape will have a big impact. And this is what I'm showing here on the right. So what I have above here is normal pentane, where I have carbons all in a line. Here I have neopentane, where I have a carbon in the middle. He's surrounded by 4 other carbons, and then the hydrogens are outside of that. They have the same molar mass, same formula, same number of electrons, but because of the shape, the spherical is more compact, so it's less polarizable. Lower dispersion forces means lower boiling point. Higher dispersion forces, easier to distort, more polarizable, higher boiling point. So you see, just the shape influences our boiling point. So this is a good demonstration of how intermolecular forces impact boiling points. The stronger the intermolecular force, the higher the boiling point. Here, these are the similar mass, same number of electrons, but have a different shape. So remember, your spherical shape is more compact, so it's harder to distort the cloud. Lower dispersion forces, lower boiling point. Okay? All right. So here's a way that we can correlate number of electrons to dispersion forces to boiling point. If something is smaller with fewer electrons, if it's harder to polarize, it's got a lower boiling point. So you can see I've got increasing boiling point on the X, and here I've got period 2, period 3, period 4, period 5 on the periodic table. If I've got smaller molecules up here, fewer electrons, lower dispersion forces, which means lower boiling point. Boiling point is going up as I go down the periodic table. Because as I go down the periodic table, I have more electrons. Makes it more polarizable, which means stronger dispersion forces, higher boiling point. We see the same thing with the halogens, F2Cl2, Br2, I2. As we go down the table, we have more electrons, they're bigger, easier to polarize, higher boiling points. This is why fluorine and chlorine are gases. At room temperature, bromine is a liquid and iodine is a solid because of intermolecular forces. All right. Our next force we're going to talk about is dipole-induced dipole. This is when you have a polar molecule next to a nonpolar neighbor. This permanent dipole can induce a dipole in his nonpolar neighbor. An ion can do the same thing. And if I have an ion here and he's next to a nonpolar molecule, he can induce a dipole in his neighbor. Ions and dipoles can do this. This is a temporary situation, just like the dispersion forces. But it still has an effect. Oh, one thing I want to mention, going back to the dispersion forces, where another place we see dispersion forces at work in real life is our plastic wrap that we use to wrap up our leftovers. The plastic wrap uses dispersion forces to hold the plastic together, to get it to stick it together, and then we can seal up our leftovers. Okay? Okay, next interaction is dipole-dipole. This is stronger than the others that we've talked about so far. Dipole-dipole interaction is when we have polar molecules with a permanent separation of charge. The oppositely charged ends will attract each other. This is a much larger intermolecular force, which translates into higher melting points and higher boiling points. So the more polar your molecule is, the higher your boiling point. So I'm going to compare 4 molecules here. They're similar size, similar shape, similar mass, but the polarity is quite different. I've got propane, which is nonpolar, dimethyl ether, acetaldehyde, acetonitrile. As I'm moving from left to right, you look at the dipole moment here, it's getting bigger. And look how that correlates with boiling point. The higher the dipole moment, the more separation of charge, the higher the boiling point. So I'm going from 231 Kelvin all the way up to 355 Kelvin. Even though the sizes and the masses are the same, this is more polar. My dipole moment is 3.9 dBs. Has a big impact on boiling point. This is dispersion forces only. And these hot 3 on the right here have dipole-dipole interactions, which makes my boiling point go up. We'll go over this in example 12.1 in the book, and that'll be fun. And then we'll move on. So let's say I have 2 molecules and I want to compare intermolecular forces. What's going to be more important, the dipole-dipole or the dispersion? Well, if your 2 molecules are similar in size, your dipole-dipole interaction will dominate behavior, like what we saw in the previous slide. But if one molecule is larger than another, dispersion forces will determine if it has a higher or lower melting point and boiling point and whatnot. For example, let's take, for example, margarine. It's a large molecule. It's nonpolar, but it's a large molecule, so it's a solid, high melting point. Okay? All right. So next we're going to talk about our next intermolecular force, but first I want to show you something here. I've got this graph. I have increasing molar mass on the x, increasing boiling point on the y. Now you see this trend here. As I go down a group at the periodic table, CH4, SiH4, GeH4, TnH4, I'm going down a group. And the molecular weight's going up, and the boiling point is going up. For these and these and these. What's going on with these guys? Well, that's weird. They're not following my trend that carbon did. What's up with that? That's weird. Well, we have an explanation for that because that's what we like to do. We like to explain things in chemistry. So what's going on here is a thing called hydrogen bonding. You get hydrogen bonding when hydrogen is bonded to a nitrogen, an oxygen, or a fluorine. These dipole-dipole interactions are especially strong. And we call those interactions hydrogen bonding. And that's why we get those super high boiling points. If we go back here we have HN, HF, HO. Those are my 3 necessary bonds that give me my high boiling points because I have a special strong intermolecular force called hydrogen bonding. Okay? So the hydrogen bonding is the attraction between a hydrogen atom on one molecule and the electronegative atom on his neighbor. So I got this illustrated here. Here, the hydrogen here is attracted to the oxygen on his neighboring molecule. Here, the hydrogen is attracted to the fluorine over here. And the nitrogen over here. Okay? So these interactions here are extremely strong because these atoms here, the oxygen, the fluorine, and the nitrogen, they're very electronegative. So they're going to have high electron density, which is going to attract the hydrogen from his neighbor. You get higher boiling points and higher melting points from your hydrogen bonding. So these are your 3 required bonds that need to be present in your molecule. It's not enough that they're both there, the bond itself has to be there. Hydrogen has to be bonded to fluorine, it has to be bonded directly to oxygen, or bonded directly to nitrogen to get this effect, the hydrogen bonding intermolecular force. It also helps explain the water's behavior when it solidifies. Why do we get this crystalline structure of, say, a snowflake? Well, what's happening is hydrogen bonding forces water to form a lattice when it freezes. And it's a very geometric lattice. And when you have these geometric lattice, you get a crystalline appearance. And this also helps to explain why water expands when it freezes. You'll notice if you pour water in your ice tray and you put it in the freezer, the ice is bigger than the water it started with. Water expands when it freezes, and this is one reason why hydrogen bonding. Water forms a lattice when it freezes. All right, in 12.2 in the book, we'll talk about hydrogen bonding and its impact on melting point. Are we going to be a solid, a liquid, or a gas at room temperature? That's why we're talking about these intermolecular forces. They help determine what phase you're in at a certain temperature, usually room temperature. All right, so now we're going to talk about our next force, ion-dipole interaction. Which actually is in your book. Nice. Okay. So this is what happens when you're forming a solution when you mix ionic compounds in water, because the water is pulling the ions apart and dissolving your solid. So this is a very strong interaction, your ion-dipole interaction, because that's what's going on when the water molecules pull the lattice apart of your ionic solid. The chlorine, or your negative ion, doesn't have to be chlorine. Your negative ion is surrounded by the positive end of water. The positive ion is surrounded by the negative end of water. This is called a solvent cage, which you'll learn more about in other chemistry classes, if you're like me and you want to take more chemistry. Okay, so here's a summary of all our intermolecular forces. We ask a series of questions to figure out what force is present. Question number 1, are there ions present? If no, go this way. Do we have a polar molecule present? If I have no ions and no polar bonds, I have dispersion forces only. If I have ions present, no. If I have polar molecules present, yes. I have to ask another question. Do I have a hydrogen bonding to nitrogen, oxygen, or fluorine? If the answer is no, I have dipole-dipole forces. If the answer is yes, I have hydrogen bonding, like with ammonia, water, ethanol, etc. A good way to figure these out is draw yourself a skeletal Lewis structure so you can visualize your connections of the atoms to form your molecule. Okay, so that's this half of the slide. Let's do the other half. Are ions present? The answer is yes. Are there polar molecules present? Like if you're dissolving them in water? The answer is yes. You've got ion-dipole forces, like when we dissolve table salt in water. If no, then we just have ions present and that's it, and we've got ionic bonding. This is your extremely, extremely strong force. Again, ionic bonds are the strongest ones, which is why salts have very high melting points. And then we'll go over a conceptual connection in the next video. We'll talk about who has the highest boiling point just based on your intermolecular forces. So you look at the polarity, if any, and do we have any hydrogen bonding, and then we can start making predictions. That's what we like to do in science. We like to make predictions. That's how we roll. All right, onward we go. So these properties, there's so many properties we've talked about are affected by intermolecular forces. We've already talked about boiling point and melting point. Next we'll talk about viscosity, surface tension, and capillary action. Okay. Viscosity is a measure of a liquid's resistance to flow. So if you flow easily, you have low viscosity. If you don't flow easily, you have high viscosity. And we generally talk about viscosity frequently in real life when we talk about our motor oil. If you have a lower rating on your motor oil, that means you have low viscosity and you could pour it faster because it flows easily when you have low viscosity. High viscosity means it doesn't want to flow so much. It pours slower. So if you have a leak in your car, you're going to want higher rating on your motor oil so it won't leak as fast. Keep in mind, though, viscosity will go down as temperature goes up. Things flow faster when they're warmer. Another good example of flow is comparing honey to water. Water flows readily. Honey, not so much. Honey has higher viscosity. Stronger intermolecular forces in the honey. Okay, another thing that is impacted by our intermolecular forces is surface tension. Surface tension is a measure of the resistance of a liquid to spread out. So you'll notice when we see rain falling and the water beads up on our car or on the cement, that's a result of surface tension. This is a surface phenomenon where the molecules on the surface are more attracted to each other than the molecules in the bulk. All right, and we see an example of this here where my little water bug is taking advantage of the surface tension of water to run across the water. So what's going on with surface tension? Like I said before, you have higher intermolecular forces at the surface. Because these guys are seeing each other really well and they're not completely surrounded. So that means the forces between them are a little bit stronger. There's your surface tension. That's your resistance to spread out. And it causes various liquids to bead up. All right, so next we're going to talk about capillary action. What's going on with capillary action is you've got a couple of different forces going on. You have cohesive forces, which are intermolecular forces that bind molecules together. Then you have adhesive forces, forces that bind a substance to a surface. As these adhesive forces is why we see a meniscus when we have water in our graduated cylinder, water in our burette, in our pipette. We get that little U shape because the water is attracted to the walls of the tube. That's called capillary action, and plants take advantage of this very well. In any case, here's an image here of water. I've colored water so I can see it better. I have this meniscus here because water is attracted to the surface of the tube. For mercury, it does the opposite, because mercury is more attracted to itself than it is to the tube. So when we have these adhesive and cohesive forces, they act to move a liquid up a tube. And this is what's going on with the roots of a tree or the roots of a plant. The plant takes advantage of the capillary action, these adhesive forces, to draw water and nutrients out of the ground and up into the plant. So how high will the water go up depends on the surface tension of your liquid and how big is your tube, and of course gravity. So you can see here in this demonstration, the more narrow the tube, the higher the liquid can travel up it. Okay. Again, plants and trees need capillary action to survive. That's what the roots are for. To take advantage of this capillary action of these adhesive forces to draw water up into the plant. Now, if you're in like kindergarten or preschool, you may have done this activity where you put a celery stalk in a cup of colored water, and through capillary action, the food coloring goes up the plant and into the leaves. You can do this with a flower too. If you put a white carnation in red water, it'll turn pink in a couple days. It's a fun STEM activity you could do at home with your child. Your child of any age, including your grown-up children. All right, so that's it for that part of the lecture. Next, we're going to talk about solubility briefly, and then we'll move on to other stuff. So solubility and intermolecular forces are very intertwined because we remember this rule we've talked about previously of like dissolves like. Polar solutes dissolve in polar solvents, so table salt dissolves in water. Nonpolar solutes dissolve in nonpolar solvents. A good example of that is your gasoline. There's a lot of nonpolar components in your gasoline because your main component is octane, which is nonpolar. All that other stuff that's also nonpolar will also dissolve in gasoline. If one liquid will dissolve in another liquid, that's called miscible. If a liquid does not dissolve in another liquid and you see layers, that's called immiscible, like oil and water in your Italian dressing. That's why you've got to give it a shake before you pour it on your salad, because you've got a water layer with the vinegar and you've got the oil layer. And they're not going to mix unless you force it and you shake the bottle. So if you have a polar compound, they're going to love water. So if you have an OH group on your compound, or an aldehyde group, a C double bond, these are all polar. Here's your carboxylic acid. If you have an amine group or even a halogen, they're going to dissolve in water because they're going to give you a polar bond. All right, so like I said a minute ago, nonpolar molecules dissolve in nonpolar solvents. Now, what you can have with some molecules, you can have part of the molecule that dissolves in water and the other part that doesn't. And we saw this with the oleic acid. The polar end of oleic acid likes the water, and the nonpolar tail will stick up in the air, and we were able to measure the length of the molecule. So if two liquids don't dissolve in each other, we get this layer. Here's an example of pentane and water. You get layers. They don't mix because they don't have the same intermolecular forces at work. Pentane is nonpolar, so it's all about the dispersion forces. Water has that OH bond. He's all about hydrogen bonding. So you need to have intermolecular forces in common to mix. Okay, and we have some trends regarding your strength in intermolecular attractions. The stronger the attraction, the more energy it takes to separate them. Hence the higher melting and boiling points. So if you want to boil a liquid, you have to overcome the intermolecular attractions. But keep in mind, the bonds that make up the molecule don't break. So the higher the boiling point, the stronger the interactive intermolecular force. So you got to put more energy in to separate the molecules from each other and get them to boil. All right, so if we are going to change from one phase to another, we have to either put energy in or energy will be released. And now we're going to go into phase changes and the intermolecular forces that affect phase changes. Melting and freezing, vaporizing and condensing. These are things we normally see in our everyday life. Something you may not have heard of before is sublimation and deposition, subliming and depositing.
We can get into the website now and add our banking information to have it direct deposit.
Okay. Sorry about that. Let's keep going. So if I want to go from solid to liquid or liquid to gas, I got to put energy in to make that happen. Those are endothermic. So we got to put water on the stove and turn on the stove to vaporize it and boil our water and cook our food. Same thing if we want to melt something. Put energy in to melt, put energy in to vaporize. Sublimation is when we go straight from solid to gas. That's called sublimation. Put energy in to do that. If you want to go the other direction, we're releasing energy. So when gas condenses to form a liquid, it releases energy. Condensation is exothermic. Freezing is exothermic. Deposition is exothermic. Now this stuff has real-world consequences, especially with the weather. If you have air with a lot of water vapor in it, and the air particle goes up, it cools, the water condenses. It releases energy when the water condenses. If you release enough energy with all that water condensing, you get high winds and hello hurricanes. Okay? When water releases energy, when it condenses in the air, it's called latent heat. The heat that's released when water condenses in the air. And that's what drives a lot of weather. Okay, so the heat involved with these energy changes. Okay, if we're melting a solid, the energy required to melt it is called the heat of fusion. If we want to boil a liquid, the energy involved is called heat of vaporization. If we want to put energy in to turn a solid directly into a gas, that's your heat of sublimation. And here in my chart below, I have various heats of fusions, vaporization, and sublimation. Here's butane, diethyl ether, here's water, here's mercury. Got put energy in to get something to melt, put energy in to get it to boil, put energy in to get it to sublimate. And water can sublimate. One place on the planet where water sublimates is the South Pole, because the air is so dry that when the snow or ice warms up, it doesn't melt, it sublimates, it goes straight into the gas phase. All right, so vaporization is the process when a liquid is converted to the gas phase. Now, what happens when we have vaporization? If we're not at the boiling point, only a small number of molecules will have enough energy to escape into the gas phase. As temperature goes up, the amount of molecules with enough energy to escape the liquid phase will go up. So you'll get more molecules in the gas phase. This is also a surface phenomenon. So the larger your surface area, the faster the evaporation, or the faster the liquid enters the gas phase. And we're going to see this in experiment 16 next week. So this is what's going on when we're vaporizing something. And we're not at the boiling point, okay? We're in the liquid phase. But here's my increasing kinetic energy on the x. Here's my fraction of molecules on the y. At a lower temperature, I have a small fraction of molecules with enough energy to escape into the gas phase. As temperature goes up, I have a higher distribution of kinetic energies, and more molecules, a higher fraction of molecules will have enough energy to escape into the gas phase. All right, if we want to go the other direction, if molecules leave the gas phase and enter the liquid phase, this is called condensation. And this can happen in two ways. A molecule can return to the liquid surface, or a few gas molecules can stick together and form a droplet. Also, what impacts vaporization and condensation is if you have an open container or a closed container. In an open container, the vapor molecules can spread out easily, faster than they condense, and they'll leave the container. In a closed container, the gas molecules have a limited area to spread out, so you get more condensation. So these are two things that can happen at the same time when you have a liquid. You have vaporization and condensation happening at the same time. The weaker the intermolecular force, the less vaporization. And the weaker the intermolecular force, the more energy is needed for a gas molecule to condense. So liquids that evaporate easily are called volatile. And the volatile liquids are the ones you can smell because they've entered the gas phase and now you can breathe them in and detect them with your nose. Like gasoline, very volatile. You can smell gasoline when you put it in your car at the gas station, right? Fingernail polish remover, acetone, volatile, escapes easily into the gas phase. If you're non-volatile, you don't escape easily into the gas phase, things like motor oil and honey. So at any temperature, some molecules will have enough energy to escape the surface and enter the gas phase. As the temperature goes up, the more molecules that enter the gas phase will increase. This will result in something called vapor pressure, because when you have these molecules in the gas phase, they will exert a pressure called vapor pressure. So if you have a closed container, here I have an evacuated flask. I'm going to put some ethanol in. I start out with nothing in the gas phase, but over time I have what's called a physical equilibrium, where I'm condensing and evaporating at the same rate. And now my total amount that stays in the gas phase is about constant, and I get what's called vapor pressure. So you get this vapor pressure when you have a closed container and you're condensing and evaporating at the same rate. Molecules are leaving the liquid phase and re-entering the liquid phase at the same rate. You get your vapor pressure. Again, this is experiment 16 stuff. Okay, so when does something boil? Well, something boils when the vapor pressure is equal to your atmospheric pressure. So if I'm at 760 torr, which is 1 atmosphere, the temperature it boils at is called the normal boiling point. So as atmospheric pressure goes down, the boiling point will go down. That's why you have your high altitude directions when you make your brownies. If you're up at Big Bear and you're making brownies, you got to follow those high altitude instructions or you're going to get lousy brownies. Okay, so as your pressure goes down with altitude, because as altitude goes up, as you go up in altitude, the vapor pressure drops. That means water doesn't boil as hot and you need to follow those high altitude directions for your brownies. Okay, so as pressure goes down, your boiling point goes down. If I'm at 1 atmosphere, 760 torr, that's called your normal boiling point. Here's water, here's ethanol, here's diethyl ether, here's ethylene glycol down here in green. He's very sticky. He's got high intermolecular forces for that guy. Okay. So, how do we relate pressure and temperature when we're talking about vapor pressure? This is called the Clausius-Clapeyron equation. This relates the pressure of your vapor and its temperature. And they're related by, here's my heat of vaporization, the energy you've got to put in to turn it into a gas. And here's our gas constant. But it's not the one we're used to seeing. This gas constant R, we're going to be using 8.314 joules per mole Kelvin. Okay, so watch your units. R can come in a lot of flavors with lots of units, but it's still R. Okay, so here's a one-point version of the Clausius-Clapeyron equation. If I plot 1 over T, that's my x, versus natural log of pressure, the slope of my line is equal to the negative heat of vaporization divided by R. Don't worry about the plus C. We don't care about that in this class. So this is your one-point Clausius-Clapeyron equation. This is your two-point version. You use the two-point version if you have 2 temperatures and 2 pressures for your liquid. You can now calculate your heat of vaporization for your compound. And this is what's going to be involved with experiment 16. You're going to watch a vapor evaporate and look at its vapor pressure versus temperature. You're going to plot that, calculate the heat of vaporization. All right, so we're going to walk through a problem that I have in the overheads here because it's not something that lends itself to pen and paper. Don't really like this problem in the book, but I do have overheads for it, so here we are. So this is 12.4 in your book, which goes over how you use data to find your heat of vaporization for your compound. So in this example 2.4, I've got dichloromethane, which is a liquid, and I've got data for it. When my dichloromethane is at these temperatures, it has these vapor pressures, and I've got instruments that can do this. I'm going to take this temperature and pressure data and calculate my heat of vaporization for my dichloromethane. Remember, this only works in a closed container. Okay? All right, so if I plot my data, I'm going to do that in Excel or whatever plotting program you like. Excel's kind of crappy. There's better ones out there. They're just not as popular or well known. But you're going to graph 1 over T. Remember, T has to be in Kelvin. And then the natural log of pressure. Find the slope of your line. So if we plot our data, the slope is negative 38.05. Set that equal to negative heat of vaporization divided by our R, 8.314. And here's my heat of vaporization that I've calculated for dichloromethane. 3.16 times 10 to the 4 joules per mole. Now your typical units for heat of vaporization will be either joules per mole or kilojoules per mole. We're going to work on an additional example from the book in another video. Okay, so that was fun. Now let's talk about a different phase we haven't talked about before. This is where this chapter gets extra cool. Supercritical fluids. So what's going on here is that when we have a gas and we apply pressure to it, we can turn it into a liquid. You may have heard of LPG, liquefied petroleum gas, That's what they're doing. They're taking a gas, they compress it with apply pressure, can compress it, turn it into a liquid. But there will be a temperature where you can't do that. It can be so hot you cannot compress it to a liquid. That's called the critical temperature. If I'm right at the critical temperature and I want to turn that gas into a liquid by applying pressure, that's called my critical pressure. So critical temperature and critical pressure is the highest temperature and the highest pressure you need to compress a gas and turn it into a liquid. If I get beyond that, higher temperatures, higher pressures, I get what's called supercritical fluid. This is an additional phase that we don't normally come across in real life, in everyday life rather. I shouldn't say real life. We don't normally come across it in everyday life, but supercritical fluids are valuable in industry because we use them as solvents to separate mixtures. So these supercritical fluids actually have really important applications, and they're very cool. So what's going on with supercritical fluids? They behave like both a liquid and a gas. They will expand to fill a container like a gas. However, they are a condensed phase. The molecules are close together. And they behave like solvents, so you can use them to separate a mixture. If you want to watch a video making a supercritical fluid, I got a video for you guys right here. I will also show this to you on Monday. It's a very cool video. Because supercritical fluids are cool. Because you know what? Science is cool. Science is not boring. Science is cool. Got all these cool videos I'm going to show you guys that show how interesting this stuff is. All right. So there's your supercritical fluids. Now we're going to move on to the energy involved in heating a solid to make a liquid, heat a liquid to make a gas. It's called a heating curve. I've got increasing heat on the X here, increasing temperature on the Y. And let's say I've got some water. Let's say I've got a block of ice. I've got to add heat to get it to the melting point. When it's at 0 degrees, I have to put in extra energy to get it to melt. That's my heat of fusion I have to overcome. The temperature will not change until all my ice is converted to water. This is why we like ice water baths in a chemistry lab. An ice water bath is a constant temperature bath. It will stay 0 degrees. And we're very good at controlling the temperature here with an ice water bath. Okay, so if you want to heat up the liquid, you put energy in. Once I get to 100 degrees for my water, I've got to put in extra energy to get it to boil. Once everything is boiled away, then the temperature can go up again. So if you've got boiling water, it stays a constant 100 degrees until all the liquid water is gone, and now you've got only steam. This is why I like to boil my chicken for dinner. You can't overcook it. It's not going to go over 100 degrees Celsius. So you're not going to have dry chicken when you're done. This is the best way to make chicken. Boil it. You cannot dry it out. You cannot overcook it because the water will not go over 100 degrees. All right. So this is a heating curve. Now, what do we do if we want to calculate the heat required to change the temperature? We're going to use our friend from our thermochemistry chapter. Q equals m times C times delta T, or Cm delta T, doesn't matter the order. Q is our heat, C is our heat capacity of our substance, m is mass, and then delta T is our change in temperature. The change in temperature should be either Celsius or Kelvin, because they have the same separation in degrees. Remember, if you're looking at change in temperature in Kelvin and change in temperature in Celsius will be the same, because they have the same separation of degrees. So if you calculate change in temperature, don't throw an extra 273 on there to turn it into Kelvin. You get the wrong answer. It's the change in temperature we're interested in. So you feel the urge to add 273, do it to initial and final temperature, not to the change. Okay? We'll go over that in class and lecture on Monday. If I'm going through a phase change, if I hit 100 degrees and I want to turn everything into a gas, my heat required is the heat of vaporization times the number of moles present. If I want to turn a liquid into a gas, if I want to turn a liquid into a solid or solid into a liquid, I use the heat of fusion. So Q, your heat required, will equal your heat of fusion times the number of moles of your substance. Now there's no good problems in the middle of the chapter on this kind of problem, but they are important. So we're going to work this question. We're going to see homework question 71 on page 536 of your book. I'm going to go over that in my other video where I'm working problems. And you'll see how to calculate the energy required if I have a block of ice and I want to convert it all the way to boiling into a gas. How much energy do I have to put in to do that? That's the kind of problem we're going to work with homework question 71. Okay, so next we're going to talk about phase diagrams. This is a fun part of that chapter. We're almost done. We're just going to do phase diagrams and call it good. All right. Phase diagrams are a way to illustrate at what temperatures and pressures do we have a solid, a liquid, or a gas. And these are going to be different for different compounds, different substances. So what I have here is your typical phase diagram that represents most compounds. Excuse me, I have to cough. Sorry. Okay, so what's going on here? I have increasing temperature on the X, increasing pressure on the Y. In my blue region here, I have my solid. Here in my dark blue region is my liquid. Here in my kind of a pink-orange area is my gas. And here's my supercritical fluid. So when I draw a line here along the temperature and pressure, this is my melting point at various pressures. This is my sublimation point. And down here, I'm going straight from solid to gas. Sublimation going this way, deposition going that way. This is what happens at low pressures. Now this I'm going to hit here, T, that's called a triple point. The triple point is where all three phases exist all at the same time. Got a very cool video for that too, where you can see a little dish of water and it's boiling and freezing and being a liquid all at once. It's very neat. So that's your triple point. You have all three phases all at the same time. Now I follow this line here. This is my melting point. I'm going from solid to liquid along this line. Here's my boiling point. My boiling point is changing as the pressure changes. I'm vaporizing, I'm condensing, I'm vaporizing, I'm condensing. Okay? When I hit this point C here, that's my critical point. If I go higher than this, higher temperature, higher pressure, I've got my supercritical fluid. Okay? Now we're going to look at a variety of phase diagrams and talk about them. Now the phase diagram for water is very interesting. He's got a low triple point. It's near 0 Celsius and a very low pressure. So we don't normally see water sublimate in everyday life, because in everyday life we're right around here. No, we're not. Where are we? We're right around. Oh, this is Celsius. All right. So we're right here. This is everyday life right here. Water's a liquid. Heat it up. Now it's a gas. Cool it down. Liquid again. Cool it down again. Solid. Okay, so we have a high critical point here for water because he has very strong intermolecular forces from that hydrogen bonding. There's one other feature I'm going to point out here. I'm going to talk about it on the next slide. One thing that's unusual for water, for the phase diagram, is my slope of my solid liquid line here. This is a negative slope. What that means is if I increase pressure, I melt. It's hard to see on this overhead. I need to find a better one. But what happens with water is if you increase pressure on ice, it'll melt. That's weird. Other substances don't do that. Water's weird. But the real world consequence of this is ice skating. When that blade puts pressure on the ice, it melts. You're not skating on ice, you're skating on a thin layer of water. Okay? It's kind of cool. Because science is cool that way. Here's another interesting phase diagram. Here's carbon dioxide. He has a high triple point. That's why we have what's called dry ice, which is solid carbon dioxide. CO2 sublimates. You cannot get a liquid in everyday life for CO2. You go straight from solid to gas. High triple point. Kind of weird. Next, we're going to look at carbon. This is a very weird phase diagram because we have several different types of solid carbon that we can get. The most common are graphite and diamond. You can also get, elemental carbon. You can get buckyballs. but carbon's a bit funky here. You see the high melting point here, close to 4,000 degrees Kelvin. And you can get gas phase carbon or liquid if you have high pressure. So the phase diagram of carbon is pretty cool. Okay, that is the end of chapter 12. And after this, a little bit later today, I will record a video on working problems. All right, I hope you were able to learn something about this intermolecular forces, molecular orbital diagrams. We talked about a lot of different stuff in this one video. That's okay. We're covering everything we need to learn for the rest of the semester. Okay, so have a good day, and I'm going to go ahead and stop recording.